Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the hidden depths of Jupiter and Saturn's atmospheres. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The telescope reveals Jupiter as a striped marble, Saturn as a golden ring bearer, both spinning in the distant cold. What the eye sees from Earth represents less than 1% of these worlds. Beneath the swirling storms that have captivated astronomers for centuries, beneath the familiar bands of cream and rust and amber, lie atmospheric depths that stretch downward for thousands upon thousands of kilometers. The visible surface storms are merely the topmost whispers of processes that unfold in crushing darkness below, in regions where the very nature of matter itself begins to transform under pressures that dwarf anything found on Earth. Jupiter's great red spot, that ancient hurricane larger than Earth itself, extends its roots deep into layers where pressure builds beyond earthly comprehension. The storm that Galileo first observed through his primitive lens in 1610 draws its power from regions where the atmosphere grows so dense that the distinction between gas and liquid begins to blur like watercolors bleeding into one another. Here, hydrogen molecules pack together under the weight of the entire planet above them, creating conditions that no laboratory on Earth has ever replicated. Conditions that exist nowhere else in human experience except in the hearts of distant gas giants. The atmospheric pressure at Jupiter's visible cloud tops measures roughly the same as Earth's at sea level, a comforting, familiar starting point that quickly becomes alien. But descend just 50 kilometers deeper into Jupiter's atmosphere, and the pressure doubles, then doubles again with the relentless mathematics of gravitational compression. At 100 kilometers down, the pressure reaches 10 times that of Earth's surface, equivalent to the crushing depths found 1 kilometer beneath Earth's oceans. At 200 kilometers, the pressure climbs to 30 Earth atmospheres. At 500 kilometers depth, hydrogen gas begins to compress into liquid hydrogen, though the transition happens so gradually, so imperceptibly, that no clear boundary exists between the gaseous and liquid states. The hydrogen and helium that make up 99% of Jupiter's atmosphere begin to behave in ways that seem to mock the familiar physics of terrestrial weather. Temperature rises steadily with depth, not from any external heat source like the sun's warming rays, but from the simple act of compression itself. As if the planet squeezes warmth from its own substance through the patient work of gravity, at depths of 1,000 kilometers, temperatures reach 340 degrees Celsius, hotter than molten lead, yet the pressure prevents the hydrogen from boiling away into space. The atmosphere becomes a furnace contained within itself, a self-heating system that has operated without pause for billions of years. Scientists still puzzle over how these deeper atmospheric layers maintain their structure across geological timespans that stretch beyond human comprehension. The storms visible from space represent only the most superficial expressions of atmospheric dynamics that operate on scales both temporal and spatial that dwarf human experience. Jupiter has been spinning for 4.5 billion years, its atmosphere in constant motion like a planetary dance that never ends, yet somehow maintaining patterns that persist across centuries with the patience of geological processes. The Great Red Spot alone has raged for at least 400 years of recorded human observation, possibly much longer, drawing energy from atmospheric layers that exist in perpetual twilight thousands of kilometers below the visible cloud tops. Only took 4 centuries of telescopic observation to realize that what appears chaotic from a distance follows rules written in the language of fluid dynamics and thermodynamics. Rules that operate with the unhurried precision of planetary mechanics. The bands of color that stripe Jupiter's face represent zones of rising and falling gas. Circulation patterns driven by the planet's rapid rotation and internal heat. Circulation that moves millions of tons of atmospheric material in flows that dwarf Earth's most powerful hurricanes. Yet these massive atmospheric rivers flow in near silence, their motion detectable only through careful measurement and patient observation across decades of study. The deeper mystery lies in what cannot be seen, what remains hidden beneath even the most powerful observations. Spacecraft like Galileo and Juno have peered into Jupiter's atmospheric depths with instruments designed to penetrate the obscuring clouds, revealing temperature and pressure profiles that hint at complexity beyond current understanding. The atmosphere extends downward until it merges imperceptibly with the planet's rocky core, if indeed such a core exists in any recognizable form. At some unknowable depth, the crushing pressure transforms hydrogen gas into something approaching a metallic liquid, a state of matter that conducts electricity like copper wire, yet flows like water, generating magnetic fields that stretch across millions of kilometers of space. These hidden atmospheric depths exist in a realm of perpetual night, illuminated only by the faint glow of compressed hydrogen heated by its own weight. Lightning occasionally flickers through these depths, electrical discharges more powerful than terrestrial lightning, yet producing only the briefest illumination in darkness that has persisted for geological ages. The lightning reveals nothing, really, except the presence of electrical activity in regions where no human instrument will ever travel, regions that remain as inaccessible as the centers of distant stars. Only took 5 billion years for gravity to create these hidden worlds within worlds, atmospheric depths that contain more hydrogen than exists in Earth's entire biosphere, compressed into states of matter that challenge the boundaries of terrestrial physics. The visible storms that dance across Jupiter's surface draw their energy from these unimaginable depths, from processes that operate beyond the reach of direct observation, beyond the comfortable scales of human experience, in the patient darkness where planetary atmospheres transform themselves according to laws older than life itself. Saturn rotates with the measured precision of a cosmic timepiece, completing each day in just 10.5 Earth hours. Yet, at its north pole, something extraordinary emerges from this rapid spin. A perfect hexagon crowns the planet's northern hemisphere, each of its 6 sides stretching longer than Earth's diameter. A geometric storm that defies the chaotic swirls and spirals that characterize most planetary weather systems. The hexagonal structure maintains its shape with mathematical precision across decades of observation, as if Saturn wears a crown carved from atmospheric dynamics that follow rules unknown to terrestrial meteorology. The hexagon extends deep into Saturn's atmosphere, its walls rising like invisible cliffs composed entirely of flowing gas. Each side of this 6-sided wonder measures approximately 13,800 kilometers in length, creating a geometric pattern that could contain multiple Earths within its boundaries. The structure rotates as a single, coherent unit, completing one full rotation every 10 hours and 39 minutes, matching exactly the rotation period of Saturn's interior radio emissions. This synchronization suggests that the hexagon connects to processes deep within the planet, atmospheric currents that extend far below the visible cloud tops into regions where pressure and temperature create conditions alien to Earth-based experience. Within the hexagon's boundaries, smaller storms swirl in complex eddies and vortices, yet they never disturb the larger geometric pattern. The hexagon's walls act like atmospheric barriers, containing weather systems that would otherwise spread across Saturn's northern hemisphere. At the very center of this geometric marvel sits a massive cyclonic storm, a hurricane-like vortex with an eye wall that could swallow Earth whole. The storm's eye measures 2,000 kilometers across, ringed by clouds that spiral inward with hypnotic regularity. Yet the hurricane remains perfectly centered within its hexagonal frame, as if the geometry itself guides the storm's behavior according to some deeper atmospheric logic. The hexagon represents one of the solar system's most puzzling meteorological phenomena, a natural structure that seems to emerge from the intersection of fluid dynamics and rotational mechanics. Laboratory experiments have created similar hexagonal patterns in rotating fluids, but only under very specific conditions involving precise ratios of rotation speed, fluid depth, and temperature gradients. Saturn somehow maintains these exact conditions across an area larger than several Earth continents, sustaining the geometric storm for decades without apparent change or decay. Scientists theorize that the hexagon forms where fast-moving atmospheric jets encounter slower-moving regions, creating standing wave patterns that lock into hexagonal geometry through the complex interplay of Coriolis forces and atmospheric pressure gradients. Only took 30 years of spacecraft observation to recognize that the hexagon changes subtly with Saturn's seasons, each of which lasts approximately 7.5 Earth years as the planet completes its leisurely 29-year orbit around the Sun. During Saturn's northern winter, the hexagon appears darker, its geometric boundaries more sharply defined against the surrounding atmospheric haze. As northern summer approaches, the structure becomes more diffuse, its edges softening as seasonal heating patterns alter the atmospheric dynamics that sustain its remarkable shape. Yet, through all these seasonal variations, the basic hexagonal pattern persists, adapting to changing conditions while maintaining its fundamental geometric identity. The hexagon exists in a realm of perpetual twilight, receiving only 1% of the sunlight that illuminates Earth's surface. At Saturn's distance from the Sun, solar heating provides insufficient energy to drive the massive atmospheric circulation patterns that maintain the hexagonal structure. Instead, the storm draws its power from Saturn's internal heat, energy left over from the planet's formation 4.5 billion years ago, supplemented by the ongoing gravitational compression of helium droplets raining through the planet's interior. This internal energy source ensures that Saturn's atmospheric dynamics operate independently of solar influences, creating weather patterns that follow rhythms measured in planetary years rather than terrestrial seasons. The geometric perfection of Saturn's hexagon challenges human intuition about natural processes, which typically produce irregular, asymmetric patterns. Nature rarely creates perfect hexagons on such enormous scales, yet Saturn maintains this geometric storm with the precision of a mathematical theorem rendered in flowing gas and atmospheric pressure. The hexagon's persistence across decades suggests that it represents a stable solution to the complex equations governing atmospheric flow on a rapidly rotating planet, a natural manifestation of mathematical principles that operate beyond human scales of space and time. Beneath the hexagon's visible structure, atmospheric currents extend downward into regions where increasing pressure and temperature transform the familiar properties of hydrogen and helium gas. The geometric storm's roots may reach hundreds or even thousands of kilometers deep, anchored in atmospheric layers where gas begins its gradual transition toward liquid, where the hexagonal pattern draws stability from Saturn's deep interior dynamics. These hidden depths remain inaccessible to direct observation, their properties inferred only through careful analysis of gravitational measurements and magnetic field variations that hint at complex processes occurring far below the visible storm. Only took billions of years for Saturn's rotation and atmospheric composition to achieve the precise conditions necessary for hexagonal storm formation, a cosmic coincidence that creates one of the solar system's most geometrically perfect natural structures. The hexagon rotates in majestic solitude above Saturn's cloud tops, a testament to the mathematical beauty that emerges from planetary scale physics. A geometric crown that adorns the gas giant with patterns more precise than any human architecture, carved from hydrogen and helium by the patient work of atmospheric dynamics operating across astronomical scales of space and time. Deep within Jupiter and Saturn, in regions where spacecraft will never venture and telescopes cannot penetrate, hydrogen undergoes a transformation that would mystify the ancient alchemists who dreamed of transmuting base metals into gold. At pressures exceeding 1 million Earth atmospheres, the familiar gas that fills party balloons and fuels rocket engines abandons its molecular structure and becomes something extraordinary: metallic hydrogen, a substance that conducts electricity like copper wire yet flows like liquid mercury, existing in a state that bridges the gap between gas and metal in ways that terrestrial physics can barely comprehend. The transformation occurs gradually, imperceptibly, across thousands of kilometers of atmospheric depth. There exists no clear boundary where gaseous hydrogen ends and metallic hydrogen begins, no dramatic phase transition marked by visible change or sudden alteration in properties. Instead, the hydrogen molecules slowly surrender their individual identities under the relentless pressure of planetary gravity, their electrons becoming shared among countless atoms in a sea of metallic conductivity that extends through the hearts of both gas giants. This metallic hydrogen ocean comprises the largest volume of any single substance in the solar system, dwarfing Earth's oceans, continents, and atmosphere combined into insignificance. Within Jupiter's core, this metallic hydrogen sea rotates with the planet's rapid 10-hour spin, carrying electrical currents that generate magnetic fields 20,000 times stronger than Earth's protective magnetosphere. The flowing metallic hydrogen acts as a planetary dynamo, converting the mechanical energy of rotation into magnetic field strength that extends millions of kilometers into space, deflecting solar wind particles and cosmic radiation with invisible barriers more powerful than any human-engineered magnetic containment system. The magnetic field lines stretch so far from Jupiter that they could encompass the Sun if Earth's star were placed at Jupiter's center, creating a magnetosphere that dominates the space around all 4 of Jupiter's largest moons. Saturn's metallic hydrogen core generates a magnetic field nearly perfectly aligned with the planet's rotational axis, an almost unique characteristic among solar system bodies that typically shows significant magnetic field tilts and wobbles. This near-perfect alignment suggests that Saturn's internal structure differs fundamentally from Jupiter's, possibly indicating variations in the formation processes that created these gas giants 4.5 billion years ago. The metallic hydrogen within Saturn rotates with clockwork precision, maintaining magnetic field stability that has persisted across geological timescales, creating a cosmic compass that points true to Saturn's rotational north with unwavering accuracy. The metallic hydrogen state represents a form of matter that exists nowhere else in the solar system under natural conditions, requiring pressures and temperatures that can only be achieved in the cores of massive planets. Laboratory attempts to create metallic hydrogen on Earth have succeeded only briefly. Under extreme conditions that barely hint at the vast metallic oceans that flow within Jupiter and Saturn's interiors, these laboratory samples exist for microseconds before the immense pressures required for their creation destroy the experimental apparatus, providing only fleeting glimpses of the material state that dominates the internal structure of gas giants across the galaxy. Only took 4.5 billion years for gravitational compression to create these metallic hydrogen seas, transforming the simple 2-atom hydrogen molecules of the early solar nebula into electrically conductive fluids that generate planetary magnetic fields stronger than stellar magnetic phenomena. The metallic hydrogen flows in convection currents driven by internal heat, rising and falling in circulation patterns that span thousands of kilometers and operate across timescales measured in millions of years. These vast currents carry heat from the planetary cores toward the surface, contributing to the internal energy that powers atmospheric storms and maintains the complex weather systems visible from space. The electrical conductivity of metallic hydrogen approaches that of liquid mercury, allowing electrical currents to flow with minimal resistance through regions larger than Earth's entire volume. These currents create magnetic field variations that spacecraft instruments can detect from millions of kilometers away, providing the only direct evidence of conditions within the otherwise inaccessible planetary cores. The Juno spacecraft, orbiting Jupiter in a highly elliptical path, measures minute variations in Jupiter's magnetic field that reveal the complex flow patterns of metallic hydrogen thousands of kilometers below the visible surface, mapping an alien ocean through its electromagnetic signatures. Scientists theorize that metallic hydrogen may exhibit properties beyond simple electrical conductivity, possibly demonstrating quantum mechanical behaviors on planetary scales that have no terrestrial analog. The enormous volumes of metallic hydrogen within gas giant cores may support quantum phenomena that operate across distances measured in thousands of kilometers, creating coherent quantum states that persist for geological time periods. Such quantum coherence, if it exists, would represent the largest quantum mechanical system in the known universe, a macroscopic manifestation of quantum physics that dwarfs all laboratory quantum systems by factors of trillions. Only took the patient work of gravitational compression across billions of years to create these hidden metallic oceans, transforming hydrogen from the lightest, simplest element into dense, electrically active fluids that generate magnetic phenomena detectable across interplanetary distances. The metallic hydrogen hearts of Jupiter and Saturn beat with electromagnetic pulses that have echoed through space since the formation of the solar system, creating magnetic field rhythms that mark time on scales beyond human comprehension, in depths where matter itself adopts forms unknown to terrestrial experience, flowing in darkness beneath atmospheric layers that stretch toward infinity. In the twilight depths of Jupiter's atmosphere, where pressure transforms the familiar into the alien, crystals of ammonia form and drift downward like snow in a winter that has lasted for billions of years. These ammonia snowflakes fall through atmospheric layers where temperatures hover around -145 degrees Celsius, each crystal growing in the darkness as it tumbles through increasingly dense hydrogen and helium gas. The snow falls steadily, silently, accumulating in drifts that span continents before melting again in the warmer depths below, only to evaporate and rise once more in a cycle of precipitation that operates on planetary scales across geological time. Deeper within Jupiter's atmosphere, in regions where pressure climbs beyond 100,000 Earth atmospheres, carbon atoms stripped from methane molecules undergo compression so intense that they crystallize into diamonds. These microscopic gems form spontaneously from atmospheric carbon, growing in the crushing depths where temperature and pressure create conditions that rival those found in Earth's mantle. The diamond rain falls through Jupiter's interior in glittering streams, each tiny crystal carrying carbon that may have originated in the solar nebula 4.5 billion years ago, compressed now into the hardest natural substance known to terrestrial science. Saturn experiences its own alien precipitation in the form of liquid helium droplets that condense from the planet's hydrogen-helium atmosphere and sink slowly toward the core like droplets of liquid metal falling through cosmic honey. These helium raindrops form when the atmosphere cools below a critical temperature threshold, causing helium to separate from hydrogen in a process similar to oil separating from water, but occurring across atmospheric volumes larger than Earth's entire biosphere. The falling helium releases gravitational potential energy as it sinks, generating heat that warms Saturn's interior and contributes to the planet's mysterious excess thermal emission, making Saturn radiate 3 times more energy than it receives from the distant Sun. The ammonia snow of Jupiter's middle atmosphere creates clouds that stretch across zones wider than Earth's continental masses, white crystalline formations that appear as pale bands in telescopic images taken from Earth. These ammonia cloud decks exist in atmospheric layers where convection carries material upward from the warmer depths below, where rising currents of hydrogen gas transport ammonia vapor toward regions cold enough for crystallization. The snow forms in towering thunderstorms that dwarf terrestrial weather systems, cumulonimbus clouds that rise hundreds of kilometers above Jupiter's average cloud level, their tops reaching into the stratosphere where solar ultraviolet radiation breaks apart ammonia molecules and creates the complex photochemical hazes that give Jupiter its distinctive coloration. Only took millions of years for these precipitation cycles to establish their rhythms, each snowfall and diamond formation representing one small episode in atmospheric processes that operate with the patience of geological time. The ammonia, snow falls and melts and evaporates and condenses again in cycles that have repeated countless times since Jupiter's formation. Each cycle moving trace amounts of material through atmospheric layers in the slow work of planetary circulation. The diamond rain accumulates in sediments that may form diamond layers within Jupiter's core, compressed carbon archives that preserve the chemical history of the early solar system in crystalline structures harder than any terrestrial mineral. The helium rain within Saturn operates as a planetary cooling mechanism, slowly draining helium from the upper atmosphere and concentrating it in the planet's interior where gravitational compression converts the element's potential energy into heat. This helium differentiation process began billions of years ago when Saturn's interior cooled sufficiently for helium to become immiscible with hydrogen, starting a rain that may continue for billions of years into the future. Each falling helium droplet carries a tiny fraction of Saturn's thermal history, a microscopic record of the planet's gradual cooling from its initial formation temperature towards some distant equilibrium state that will not be reached for eons to come. Scientists calculate that Jupiter's diamond rain may produce more diamonds in a single year than exist in all of Earth's diamond mines combined. Yet these gems remain forever inaccessible in the crushing depths where no spacecraft could survive and no drilling technology could reach. The diamonds form, accumulate, and possibly dissolve again in the even greater pressures of Jupiter's deepest interior. Their existence inferred only through laboratory experiments that recreate Jovian conditions for microseconds in chambers designed to contain pressures that would destroy any conventional material. The diamond rain represents nature's largest gemstone factory, operating in darkness and isolation, producing crystalline beauty that will never be seen by human eyes. The precipitation patterns within gas giant atmospheres follow chemical rules that govern the behavior of matter under extreme conditions, rules that dictate when ammonia crystallizes, when carbon forms diamonds, when helium separates from hydrogen in cosmic processes that transform simple elements into complex structures through the patient application of pressure and time. These alien forms of precipitation occur in atmospheric volumes so vast that Earth's entire biosphere could be contained within a single thunderstorm. Yet they operate with the delicate precision of molecular chemistry, building crystals atom by atom in the darkness between worlds. Only took billions of years for gravity to create the conditions necessary for these exotic forms of precipitation, compressing planetary atmospheres until familiar elements adopt unfamiliar behaviors, until the simple chemistry of hydrogen, helium, carbon, and nitrogen becomes the complex artistry of diamond formation and helium rain. Crystalline beauty emerging from atmospheric dynamics that operate beyond human scales of space and time. In the hidden depths where planets practice their own forms of slow, patient alchemy. The Great Red Spot has gazed upward from Jupiter's southern hemisphere for at least 4 centuries of human observation, possibly much longer. Its rust-colored eye measuring wider than Earth itself, yet representing only the visible surface of a storm system whose true dimensions extend thousands of kilometers deeper into the planet's atmospheric interior. This ancient hurricane draws its longevity not from the thin surface winds that spacecraft observe, but from routes that penetrate far below the ammonia cloud tops, anchored in atmospheric layers where pressure and temperature create conditions that sustain perpetual motion across geological timescales. Unlike terrestrial hurricanes that derive their energy from warm ocean surfaces and dissipate quickly when they encounter land, Jupiter's Great Red Spot feeds on the planet's internal heat, drawing energy from convection currents that rise from depths where atmospheric pressure exceeds 1,000 Earth atmospheres. The storm's deep roots tap into Jupiter's vast reservoir of internal thermal energy, energy generated by the planet's ongoing gravitational compression and the slow cooling that has continued since Jupiter's formation 4.5 billion years ago. This connection to the planet's interior gives the Great Red Spot access to an energy source that dwarfs any terrestrial weather system, explaining how the storm maintains its intensity across centuries while Earth's most powerful hurricanes last mere weeks. The storm's visible surface rotates counterclockwise with wind speeds that reach 500 kilometers per hour. Yet these surface winds represent only the topmost circulation of a vortex that extends downward through atmospheric layers, where hydrogen gas gradually transitions toward liquid hydrogen under increasing pressure. The Great Red Spot's circulation creates a vertical column of rotating atmospheric material that may extend 3,000 kilometers deep, reaching into regions where the distinction between Jupiter's atmosphere and interior begins to blur into arbitrary definitions of planetary structure. Recent observations from the Juno spacecraft reveal that the Great Red Spot's roots penetrate far deeper than previously imagined, extending into atmospheric layers where gravitational measurements detect mass anomalies associated with the storm's circulation. These deep roots anchor the storm against the shearing forces of Jupiter's rapid rotation, which would otherwise tear apart any surface weather system through differential rotation effects. The storm's deep structure creates a stabilizing mechanism that allows it to persist despite existing on a planet where the equatorial regions complete each rotation 40 minutes faster than the polar regions, creating wind shear forces that would destroy any shallow atmospheric disturbance. The Great Red Spot shrinks and expands in cycles that operate across decades, sometimes measuring 3 Earth diameters wide, sometimes contracting to barely 1.5 Earth diameters, yet never disappearing entirely despite predictions of its imminent dissolution. These size variations reflect complex interactions between the storm and Jupiter's broader atmospheric circulation patterns, interactions that involve the exchange of angular momentum between the Great Red Spot and the jet streams that flow around Jupiter's equatorial and temperate regions. The storm breathes like a living organism, contracting and expanding as it exchanges energy and momentum with the surrounding atmosphere across timescales that span human generations. Only took 400 years of telescopic observation to realize that the Great Red Spot represents far more than a simple atmospheric storm, revealing itself instead as a quasi-permanent feature of Jupiter's atmospheric dynamics, a self-sustaining vortex that has outlasted entire civilizations on Earth while maintaining its basic structure and position. The storm drifts slowly in longitude, completing one full circuit around Jupiter approximately every 6 Earth years. Yet this apparent motion masks the storm's fundamental stability within Jupiter's complex atmospheric flow patterns. The reddish coloration that gives the storm its name results from complex photochemical processes that occur when solar ultraviolet radiation interacts with atmospheric compounds raised from Jupiter's deeper layers by the storm's circulation. The red chromophores that color the storm may be organic compounds created through the interaction of sunlight with phosphine, ammonia, and hydrogen sulfide gases brought up from the planet's interior, creating a vast atmospheric chemistry laboratory where sunlight drives reactions that have no terrestrial analog. The storm's color variations across its surface map the three-dimensional structure of its circulation, revealing upwelling regions where material rises from below and downwelling regions where surface material sinks back into the depths. Scientists theorize that Jupiter may host multiple deep-rooted storms similar to the Great Red Spot, atmospheric vortices that exist primarily in the planet's deeper layers and occasionally manifest visible surface expressions that human observers can detect and study. These hidden storms may operate as energy transfer mechanisms that move heat from Jupiter's interior toward its surface, contributing to the planet's thermal emission while remaining largely invisible to external observation. The Great Red Spot may represent the most prominent example of a broader class of atmospheric phenomena that operate in the deep atmospheres of gas giant planets throughout the galaxy. The storm's persistence across centuries demonstrates the remarkable stability that atmospheric systems can achieve when they access energy sources on planetary scales, when they extend their influence across atmospheric layers measured in thousands of kilometers depth. When they operate in environments where the fundamental properties of matter itself change with depth, only took billions of years for Jupiter's internal structure and atmospheric composition to evolve conditions capable of sustaining such persistent vortices, creating a planetary environment where storms can achieve the longevity of geological features while maintaining the dynamic complexity of active weather systems. The Great Red Spot rotates in its eternal vigil above Jupiter's cloud tops, a visible manifestation of atmospheric processes that operate in depths where human understanding reaches its limits, where the physics of rotating fluids under extreme pressure creates phenomena that challenge terrestrial analogies. In the patient darkness, where planetary storms draw energy from sources older than life itself, within the metallic hydrogen cores of Jupiter and Saturn, vast electrical currents flow in patterns that transform these gas giants into the most powerful electromagnetic generators in the solar system, creating magnetic fields that stretch across millions of kilometers of space with strength that dwarfs Earth's protective magnetosphere by factors of thousands. These planetary dynamos operate through the rotation of electrically conductive metallic hydrogen, converting the mechanical energy of planetary spin into magnetic field energy that shapes the space environment around each gas giant, deflecting cosmic radiation and solar wind particles with invisible barriers more powerful than any human-engineered magnetic containment system. Jupiter's magnetic field emerges from electrical currents flowing through metallic hydrogen regions that extend from approximately 0.7 to 0.9 Jupiter radii from the planet's center, a vast spherical shell of conducting fluid that rotates with the planet's rapid 10-hour period. The flowing metallic hydrogen acts as a liquid electrical conductor larger than Earth itself, generating magnetic fields through dynamo processes that operate on scales impossible to replicate in terrestrial laboratories. The magnetic field strength at Jupiter's cloud tops reaches 4.3 Gauss, nearly 10 times stronger than Earth's surface magnetic field. Yet this represents only a fraction of the field strength that exists deep within the planet's metallic hydrogen core. The magnetic field lines that emerge from Jupiter's metallic hydrogen dynamo stretch so far into space that they encompass all four of Jupiter's largest moons, Io, Europa, Ganymede, and Callisto within a magnetosphere that could contain the Sun if Earth's star were placed at Jupiter's center. This enormous magnetic bubble deflects most cosmic radiation and solar wind particles, but it also traps high-energy particles in radiation belts that make Jupiter's magnetosphere one of the most radioactive environments in the solar system. Spacecraft venturing into Jupiter's inner magnetosphere must be heavily shielded against radiation levels that would be lethal to unprotected humans within minutes of exposure. Saturn's magnetic field demonstrates remarkable precision in its alignment with the planet's rotational axis, showing less than 0.1 degrees of tilt between magnetic and rotational poles, an almost unique characteristic among solar system bodies that typically exhibit significant magnetic field wobbles and variations. This near-perfect alignment suggests that Saturn's internal dynamo operates with extraordinary stability, possibly indicating fundamental differences in the planet's internal structure compared to Jupiter's more chaotic magnetic field geometry. The magnetic field precision implies that Saturn's metallic hydrogen core rotates as a nearly solid unit, maintaining coherent electrical currents across volumes larger than Earth's entire biosphere. Only took billions of years for gravitational compression to create the conditions necessary for metallic hydrogen formation, transforming simple hydrogen molecules into electrically conductive fluids through pressures that exceed 1 million Earth atmospheres. The metallic hydrogen dynamo regions within both planets operate as self-sustaining electromagnetic systems, converting rotational energy into magnetic field energy through processes that have continued without interruption since the planet's formation 4.5 billion years ago. These dynamos represent the largest electromagnetic machines in the solar system, generating magnetic phenomena that influence the behavior of charged particles across interplanetary distances. The electrical currents flowing through Jupiter's metallic hydrogen core carry approximately 400 million amperes of current, electrical flows that dwarf the most powerful terrestrial electrical systems by factors of millions. These currents generate magnetic field energy equivalent to the power output of thousands of nuclear reactors. Yet the energy dissipation occurs across volumes so vast that the metallic hydrogen experiences virtually no resistive heating from its electromagnetic activity. The dynamo operates with an efficiency that approaches theoretical perfection, converting mechanical rotation into magnetic field energy with minimal energy loss across geological timescales. Saturn's magnetic field exhibits variations that correlate with the planet's mysterious radio emissions, electromagnetic pulses that were initially interpreted as evidence of planetary rotation period, but may actually reflect complex interactions between the magnetic field and Saturn's ring system. The radio emission suggests that Saturn's magnetosphere responds dynamically to changes in the charged particle environment around the planet, possibly influenced by material ejected from Saturn's moons or variations in solar wind pressure that alter the magnetosphere's boundary conditions. These radio signals provide the only direct evidence of electromagnetic activity within Saturn's otherwise inaccessible interior. The magnetic field generators within Jupiter and Saturn operate through magnetohydrodynamic processes that couple the motion of electrically conductive fluids with magnetic field generation, creating feedback systems where magnetic fields influence fluid motion, and fluid motion generates magnetic fields in complex, nonlinear interactions. These magnetohydrodynamic dynamos maintain their stability across billions of years despite operating in highly turbulent, rapidly rotating environments where small perturbations might be expected to grow into chaotic instabilities that would destroy coherent magnetic field generation. Scientists theorize that the metallic hydrogen dynamos within gas giant planets may exhibit quantum mechanical properties on macroscopic scales, possibly supporting quantum coherence effects across distances measured in thousands of kilometers. Such quantum behavior, if it exists, would represent the largest quantum mechanical system in the known universe, a macroscopic manifestation of quantum physics that operates through electromagnetic interactions involving more particles than exist in Earth's entire biosphere. The quantum properties of metallic hydrogen remain largely theoretical, inferred from laboratory studies of hydrogen under extreme pressure that hint at exotic quantum states that may emerge under the conditions found in gas giant interiors. Only took the patient work of planetary formation and gravitational compression to create these electromagnetic generators, transforming hydrogen from the simplest, lightest element into dense, electrically active fluids that generate magnetic phenomena detectable across the solar system. Magnetic field generators that operate with the precision of cosmic clockwork in the hidden depths where matter adopts forms unknown to terrestrial experience. Within Saturn's hydrogen-helium atmosphere, liquid helium droplets condense from the gaseous mixture and begin a slow descent toward the planet's core, falling like metallic rain through atmospheric layers where pressure and temperature create conditions that allow helium to separate from hydrogen in a process that has operated continuously for billions of years. These helium raindrops sink through Saturn's interior with the patience of geological time, each droplet carrying gravitational potential energy that converts to heat as it falls, creating an internal energy source that makes Saturn radiate 2.3 times more thermal energy than it receives from the distant Sun, transforming the planet into a self-warming world powered by the simple act of elemental separation. The helium rain phenomenon begins in Saturn's upper atmosphere, where temperatures drop below approximately 2000 Kelvin, a critical threshold where helium becomes immiscible with hydrogen under the pressure conditions found within Saturn's interior. At this temperature, helium atoms lose their ability to remain dissolved in the hydrogen medium, much like oil separating from water when the mixture cools, except this separation occurs across atmospheric volumes larger than Earth's entire biosphere. The phase separation proceeds gradually, imperceptibly, as helium atoms aggregate into microscopic droplets that grow larger through collision and coalescence until gravitational forces overcome atmospheric buoyancy and the droplets begin their long journey towards Saturn's core. Each falling helium droplet releases approximately 2 times its rest mass energy equivalent as it sinks through Saturn's gravitational field. Though this energy release occurs so gradually, across such vast distances and time spans, that the process operates more like a planetary heating system than an explosive energy release. The helium rain converts gravitational potential energy into thermal energy through a mechanism similar to the Kelvin-Helmholtz contraction that powers brown dwarf stars, except that Saturn's helium differentiation process operates at lower temperatures and pressures, creating a gentle, sustained heating that has warmed the planet's interior for approximately 2 billion years since the helium rain began. Saturn's excess thermal emission puzzled astronomers for decades before the helium rain mechanism provided a satisfactory explanation for the planet's anomalous energy budget. Unlike Jupiter, which radiates excess energy primarily through leftover heat from its initial formation and ongoing gravitational compression, Saturn derives a significant fraction of its thermal emission from the ongoing helium differentiation process that slowly concentrates helium in the planet's interior while depleting helium from the outer atmospheric layers. This process operates as a form of planetary distillation, separating Saturn's original hydrogen-helium mixture into distinct layers with different compositions and densities. The helium droplets that form in Saturn's atmosphere measure only micrometers in diameter initially, smaller than particles of talcum powder, yet they grow through collision and coalescence as they fall through increasingly dense atmospheric layers. In the deeper regions of Saturn's atmosphere, where pressure climbs to thousands of Earth atmospheres, the helium droplets may reach sizes measured in millimeters or even centimeters. metallic spheres of liquid helium that fall through liquid metallic hydrogen like steel ball bearings dropping through honey. Their fall rate determined by the complex interplay of gravitational acceleration, atmospheric drag, and the changing properties of the medium through which they descend. Only took approximately 2 billion years for Saturn's interior to cool sufficiently for helium rain to begin, marking a transition in the planet's thermal evolution from a Jupiter-like state where helium remained dissolved in hydrogen to the current era of elemental differentiation that may continue for billions of years into the future. The onset of helium rain represents a kind of planetary middle age, a stage in Saturn's evolution where internal processes shift from rapid cooling and contraction toward the slower, more subtle energy release mechanisms that characterize mature gas giant planets. The helium rain creates compositional gradients within Saturn's interior that influence the planet's overall density structure and gravitational field characteristics. As helium concentrates in the deeper layers, Saturn's core becomes increasingly helium-rich, while the outer atmospheric layers become progressively helium-depleted, creating a planetary stratification that spacecraft instruments can detect through precise measurements of gravitational anomalies and atmospheric composition profiles. The Cassini mission revealed that Saturn's upper atmosphere contains only about 7% helium by mass, significantly less than the solar abundance of approximately 25% helium, providing direct evidence of the helium depletion caused by billions of years of helium rain. The thermal energy released by helium rain contributes to Saturn's atmospheric dynamics, driving convection currents that transport heat from the planet's interior toward the surface and influence the formation of the complex weather patterns visible in Saturn's cloud systems. The energy from helium differentiation may power some of Saturn's atmospheric storms, including the massive hexagonal storm system at the planet's north pole and the great white spot storms that appear periodically in Saturn's temperate latitudes. The helium rain thus links Saturn's interior evolution to its atmospheric behavior, creating feedback mechanisms that operate across planetary scales and geological timespans. Scientists calculate that Saturn's helium rain may continue for approximately another billion years before the helium differentiation process reaches equilibrium, at which point Saturn will have segregated most of its helium into the planet's core region while leaving the outer atmosphere composed almost entirely of hydrogen. This represents only the most recent chapter in Saturn's thermal evolution, a phase of planetary cooling that began when Saturn first formed from the collapse of the solar nebula and will continue until the planet reaches thermal equilibrium with its space environment billions of years in the future. The helium droplets fall in perpetual silence through atmospheric depths where no sound can propagate. Their motion, detectable only through the thermal signature they create as gravitational potential energy, converts to heat in the patient darkness, where planetary interiors practice their own forms of slow, elemental alchemy across time, scales that dwarf human comprehension. Both Jupiter and Saturn harbor a profound atmospheric mystery that challenges current theories of planetary formation. They contain significantly less water than theoretical models predict, a chemical deficit that hints at complex formation histories involving processes that remain poorly understood despite decades of spacecraft observations and laboratory studies. The missing water represents one of the most significant discrepancies between observed planetary compositions and the chemical models that attempt to explain how gas giants formed from the primordial solar nebula 4.5 billion years ago, when the young sun was surrounded by a disk of hydrogen, helium, water ice, and rocky material that eventually condensed into the planets that orbit our star today. Jupiter's atmosphere contains only about half the expected water abundance based on solar composition ratios, a shortage that amounts to billions of tons of missing H2O molecules that should exist somewhere within the planet's vast atmospheric inventory if Jupiter formed according to the standard core accretion model. The Galileo atmospheric probe, which plunged into Jupiter's atmosphere in 1995, measured water concentrations in the planet's upper atmospheric layers, but found values far below the expected solar abundance ratios. This water deficit suggests either that Jupiter formed under conditions different from current theoretical assumptions, or that water exists in forms and locations within the planet that remain inaccessible to current observational techniques. Saturn exhibits an even more pronounced water shortage, with atmospheric water concentrations that fall below even Jupiter's depleted levels, creating a puzzle that deepens as measurement precision improves through increasingly sophisticated spacecraft instruments. The Cassini mission's detailed atmospheric studies confirmed that Saturn's observable atmosphere contains water ice crystals in specific cloud layers, but the overall water abundance remains mysteriously low compared to the cosmic abundance ratios that characterize the solar system's overall chemical composition. This water deficit cannot be explained by simple loss mechanisms, since both planets possess gravitational fields strong enough to retain water molecules against thermal escape or solar wind stripping. The missing water may exist in forms that current instruments cannot easily detect, possibly incorporated into complex atmospheric chemistry that transforms water molecules into other compounds through photochemical reactions driven by solar ultraviolet radiation or high-energy particle interactions within the planet's magnetospheres. Water molecules in the deeper atmospheric layers of both gas giants experience pressures and temperatures that may force them into exotic chemical states or physical phases that differ dramatically from the familiar solid, liquid, and gaseous phases of water found on Earth. Under the extreme conditions found in gas giant atmospheres, water may adopt molecular configurations that escape detection by conventional spectroscopic techniques. Only took 4.5 billion years for these atmospheric water deficits to develop, either through formation processes that preferentially excluded water from the gas giant's atmospheric inventories, or through subsequent chemical evolution that transformed primordial water into unrecognizable molecular configurations. The water shortage suggests that Jupiter and Saturn may have formed through rapid gas accretion processes that occurred before water-rich planetesimals could be fully incorporated into the growing planetary masses. Or alternatively, that the planets migrated through the early solar system in ways that affected their ability to capture and retain water-bearing material from the solar nebula. The search for Jupiter's missing water has motivated increasingly sophisticated atmospheric probe missions designed to penetrate deeper into the planet's atmosphere than previous spacecraft have achieved. The Juno mission carries microwave radiometry instruments capable of detecting water vapor in atmospheric layers previously inaccessible to remote sensing, revealing water abundance variations that correlate with Jupiter's complex atmospheric circulation patterns. These measurements suggest that water may be distributed heterogeneously throughout Jupiter's atmosphere, concentrated in specific regions or atmospheric layers in ways that make global abundance estimates difficult to determine from limited sampling. Saturn's water mystery deepens with the recognition that the planet's rings contain significant amounts of water ice, yet this water appears to be compositionally distinct from any water that might exist in Saturn's atmosphere, suggesting different sources or formation mechanisms for ring material versus atmospheric constituents. The ring water may represent material captured from external sources such as comets or icy moons, while the atmospheric water deficit reflects original formation conditions or subsequent chemical evolution processes that operated on entirely different timescales and through different physical mechanisms. Scientists theorize that both planets may contain vast reservoirs of water in chemical forms that remain difficult to detect through conventional atmospheric analysis techniques. Water molecules under the extreme pressure and temperature conditions found in gas giant interiors may dissociate into hydrogen and oxygen atoms that become incorporated into the planet's overall atmospheric chemistry in ways that obscure their original identity as water molecules. The hydrogen from dissociated water becomes indistinguishable from the vast quantities of hydrogen that comprise the bulk of both planets' atmospheric masses. While the oxygen may form chemical compounds with carbon, nitrogen, or sulfur that create complex atmospheric chemistry networks, the missing water puzzle extends beyond Jupiter and Saturn to other gas giant planets throughout the galaxy, suggesting that water deficits may represent a common characteristic of planetary formation processes rather than an anomaly specific to our solar system. Exoplanet atmospheric studies have revealed similar water shortages in hot Jupiter planets orbiting other stars, indicating that the physical and chemical processes responsible for water depletion operate across a wide range of planetary formation environments and stellar system architectures. Only took decades of increasingly sophisticated atmospheric measurements to recognize the extent of the water deficit problem, revealing that these gas giants guard their chemical secrets in atmospheric depths, where pressure and temperature create conditions that transform familiar molecules into exotic configurations. In the patient darkness where planetary formation mysteries persist across billions of years, waiting for instruments sensitive enough to detect water in forms that challenge human assumptions about atmospheric chemistry and planetary evolution. Lightning illuminates the darkness within Jupiter and Saturn's atmospheric depths with electrical discharges 1,000 times more powerful than terrestrial thunderstorms, creating brief moments of brilliant illumination in regions where no sunlight has penetrated for billions of years. These alien lightning bolts carry electrical currents measured in millions of amperes, generating electromagnetic pulses that spacecraft can detect from distances of millions of kilometers. Radio signals that announce the presence of atmospheric electrical activity operating on scales that dwarf any weather phenomenon found on Earth. The lightning forms in towering thunderstorms that rise hundreds of kilometers above the planet's average cloud levels. Cumulonimbus structures so vast that Earth's most powerful hurricanes would appear as minor disturbances in comparison. Jupiter's lightning emerges from water cloud layers located approximately 50 kilometers below the visible ammonia cloud tops, in atmospheric regions where pressure climbs to 5 Earth atmospheres and temperatures reach the freezing point of water. These deep water clouds provide the moisture necessary for thunderstorm formation, creating convective systems that transport electrical charge across vertical distances measured in hundreds of kilometers. The lightning discharges occur within storm systems that may persist for weeks or months. Electrical activity that continues long after terrestrial thunderstorms would have dissipated their energy, sustained by the vast atmospheric volumes and energy sources available within gas giant weather systems. The electrical activity within Saturn's atmosphere generates lightning strokes that produce radio emissions detectable by spacecraft instruments orbiting millions of kilometers away from the planet. Electromagnetic signatures that reveal the presence of atmospheric electrical phenomena operating in regions completely inaccessible to direct observation. Saturn's lightning appears to concentrate in specific latitude bands, where atmospheric dynamics create conditions favorable for electrical charge separation, regions where rising and falling atmospheric currents generate the charge gradients necessary for lightning formation. The lightning frequency varies with Saturn's seasons, increasing during periods when solar heating creates enhanced atmospheric convection in the planet's summer hemisphere. Each lightning discharge within these gas giant atmospheres releases energy equivalent to several billion joules, electrical phenomena that briefly achieve temperatures exceeding 30,000 Kelvin, hotter than the surface of the Sun, creating plasma channels that expand explosively through the surrounding hydrogen-helium atmosphere. The lightning channels exist for only milliseconds before cooling and disappearing back into the atmospheric darkness, But during their brief existence, they create conditions of temperature and pressure that approach those found in stellar interiors, transforming ordinary atmospheric gas into exotic plasma states that exist nowhere else in the solar system under natural conditions. The electrical charge separation that powers these lightning systems operates through atmospheric convection processes that transport water ice crystals and ammonia particles across vast vertical distances within towering storm systems. As ice particles collide and separate within these convective currents, they exchange electrical charge through triboelectric effects similar to those that generate static electricity when synthetic fabrics rub together, except that the charge separation occurs across atmospheric volumes larger than Earth's continental masses. The resulting electrical potential differences can reach billions of volts, creating electric fields strong enough to accelerate charged particles to velocities approaching the speed of light. Only took millions of years for these atmospheric electrical systems to establish their complex patterns of charge separation and discharge. Each lightning stroke representing one brief moment in electrical processes that have operated continuously since the planet's atmospheric structures stabilized after their initial formation. The lightning frequency varies with atmospheric dynamics driven by seasonal changes, internal heat transport, and complex interactions between atmospheric circulation patterns and the planet's rapid rotation rates. Jupiter experiences lightning discharges approximately once every few seconds somewhere within its vast atmospheric volume. While Saturn's electrical activity follows more sporadic patterns that correlate with the planet's longer seasonal cycles, the electromagnetic pulses generated by gas giant lightning create radio interference that can disrupt spacecraft communication systems, electromagnetic noise that extends across a broad spectrum of radio frequencies and propagates throughout the magnetospheres that surround both planets. These radio emissions provide scientists with a remote sensing tool for studying atmospheric electrical activity, allowing researchers to monitor lightning frequency and intensity from spacecraft positioned millions of kilometers away from the actual storm systems. The radio signals reveal that lightning activity correlates with atmospheric dynamics, increasing during periods of enhanced convection and decreasing during atmospheric stable phases. Saturn's lightning exhibits a peculiar characteristic. It appears to occur primarily on the planet's day side, concentrated in regions where solar heating drives enhanced atmospheric convection. Contrary to terrestrial lightning patterns that typically favor nighttime hours when surface cooling creates atmospheric instabilities. This dayside lightning preference suggests that Saturn's electrical activity responds directly to solar heating effects. Despite the weak solar illumination that reaches Saturn's distance from the Sun, the correlation between lightning activity and solar heating indicates that even the minimal energy input from sunlight can influence atmospheric dynamics on planets where internal heat sources dominate the overall energy budget. Scientists theorize that the lightning within gas giant atmospheres may play important roles in atmospheric chemistry, creating high-energy environments where unusual chemical reactions can occur. Reactions that might not take place under the normal temperature and pressure conditions found in planetary atmospheres. The lightning discharges may generate complex organic molecules through electrical breakdown of simple atmospheric constituents like methane, ammonia, and hydrogen, creating chemical complexity through electrical processes that operate on planetary scales across geological time periods. The lightning continues its eternal dance through atmospheric depths, where darkness has reigned since planetary formation. Electrical phenomena that briefly illuminate alien weather systems with plasma temperatures that rival stellar fusion processes. In the patient silence where atmospheric electrical activity marks time across scales that dwarf human comprehension, creating moments of brilliant illumination in depths where no human observer will ever witness the awesome electrical displays that have flickered through gas giant atmospheres for billions of years. The Juno and Cassini missions transformed human understanding of gas giant interiors through gravitational archaeology. Using precise measurements of tiny variations in spacecraft trajectories to map the internal structure of Jupiter and Saturn with unprecedented detail, revealing that these planets guard secrets in their cores that challenge fundamental assumptions about planetary formation and evolution. These spacecraft operate as extraordinarily sensitive gravitational detectors, measuring minute changes in radio signal frequency caused by variations in gravitational field strength as they orbit through the complex gravitational landscapes created by mass distributions deep within the planet's inaccessible interiors. Juno's elliptical orbit around Jupiter carries the spacecraft from distances of 4,200 kilometers above the cloud tops to millions of kilometers away, creating a gravitational measurement baseline that allows scientists to detect mass variations equivalent to differences of a few parts per billion in Jupiter's overall gravitational field. These measurements reveal that Jupiter's core extends much farther from the planet's center than theoretical models predicted, reaching perhaps halfway to the surface in a diffuse, partially dissolved structure that defies the simple, rocky core models that previously dominated planetary formation theories. The gravitational data suggests that Jupiter's core may be fuzzy or dilute, mixed with metallic hydrogen in ways that blur the distinction between core and envelope. Saturn's gravitational field, mapped in exquisite detail during Cassini's final orbital phase, reveals an internal structure that differs fundamentally from Jupiter's architecture, with a more compact, possibly more differentiated core that may retain more of its original rocky and icy composition. The gravitational measurements indicate that Saturn's core mass comprises between 15 and 18 Earth masses, significantly larger than Jupiter's core relative to the planet's total masses, suggesting different formation histories or subsequent evolutionary processes that shaped the internal structure of each gas giant according to different physical mechanisms. The gravitational archaeology technique exploits the fact that mass distributions within planetary interiors create subtle variations in gravitational field strength that influence spacecraft trajectories in measurable ways. Variations so small that they require atomic clock precision and sophisticated data analysis techniques to detect and interpret. Each gravitational measurement represents the cumulative effect of all mass within the planet. But advanced mathematical techniques allow scientists to invert the gravitational data and reconstruct three-dimensional maps of internal density variations, revealing core structures, atmospheric mass distributions, and even the deep circulation patterns that transport material through the planet's fluid interiors. Only took decades of spacecraft mission development and data analysis to achieve the measurement precision necessary for gravitational archaeology. Transforming gravitational field mapping from crude estimates based on orbital mechanics to detailed internal structure determination that reveals features within planetary cores with spatial resolution measured in hundreds of kilometers. The gravitational measurements operate like medical imaging techniques that use external signals to map internal structures, except that planetary gravitational archaeology uses the planet's own gravitational fields as the signal source and spacecraft trajectories as the detection mechanism. Juno's gravitational measurements reveal that Jupiter's zonal wind patterns, the east-west atmospheric flows that create the planet's distinctive banded appearance, extend much deeper into the planet's interior than atmospheric models predicted, reaching depths of 3,000 kilometers or more below the visible cloud tops. These deep atmospheric flows create density variations that spacecraft instruments can detect through their gravitational signatures, indicating that Jupiter's atmospheric dynamics couple strongly to internal processes operating in the planet's fluid metallic hydrogen regions. The deep wind patterns suggest that Jupiter's atmospheric circulation represents a planet-wide phenomenon that involves the entire fluid portion of the planet's interior. Saturn's gravitational field exhibits asymmetries that correlate with the planet's seasonal cycles, variations that may reflect changes in atmospheric mass distribution as seasonal heating patterns alter the global circulation of Saturn's atmosphere. These seasonal gravitational variations operate on timescales of Saturn years, approximately 29 Earth years per complete cycle, requiring decades of observation to detect and characterize fully. The seasonal gravitational changes suggest that Saturn's internal structure responds dynamically to external forcing from solar heating variations, creating coupling between atmospheric dynamics and interior processes that operates across the planet's entire fluid envelope. The gravitational data from both missions reveal that gas giant formation involved more complex processes than simple core accretion models suggest, indicating that these planets may have formed through disk instability mechanisms that created diffuse, extended cores rather than compact rocky centers. The fuzzy core structures detected through gravitational archaeology support formation scenarios where gas giants formed rapidly through gravitational collapse of dense regions within the solar nebula, creating planets with internal structures that preserve signatures of their rapid formation in the early solar system. Scientists use the gravitational measurements to constrain models of planetary interior composition, determining the relative abundances of hydrogen, helium, and heavier elements within different regions of each planet's interior through comparison of observed gravitational fields with theoretical predictions based on different compositional assumptions. These compositional models provide insights into the chemical evolution of the solar system, revealing how the distribution of elements within the solar nebula influence the formation and subsequent evolution of gas giant planets. The gravitational archaeology continues as both spacecraft accumulate additional orbital data, each gravitational measurement adding new constraints to models of internal structure and composition, gradually revealing the internal architecture of gas giants through the patient accumulation of precise trajectory measurements, in the invisible mapping of mass distributions that have remained hidden since planetary formation. Gravitational signatures that tell stories of solar system evolution written in the language of orbital mechanics and detected through the subtle influence of buried mass on spacecraft trajectories measured with atomic precision across billions of kilometers of space. Saturn's hexagonal storm system undergoes dramatic transformations during the planet's 30-year seasonal cycle, expanding and contracting its geometric boundaries as solar heating patterns shift across Saturn's tilted axis, creating seasonal atmospheric dynamics that operate on timescales longer than entire human generations. The hexagon's seasonal evolution reveals that even Saturn's most stable atmospheric features respond to the distant sun's influence, despite receiving only 1% of the solar energy that illuminates Earth's surface, demonstrating the remarkable sensitivity of atmospheric systems to minute changes in energy input when those changes operate across planetary scales and geological time spans. During Saturn's northern winter, which lasts approximately 7.5 Earth years, the hexagonal storm appears darker and more sharply defined against the surrounding atmospheric haze, its geometric boundaries etched with mathematical precision against the swirling chaos of Saturn's global circulation patterns. The winter hexagon maintains its six-sided structure with remarkable stability, each side measuring approximately 13,800 kilometers in length, creating a geometric pattern that persists through the long polar night when Saturn's northern hemisphere receives no direct solar illumination for years at a time. The hexagon's winter configuration suggests that the geometric storm draws its primary energy from Saturn's internal heat rather than solar heating, operating as a manifestation of the planet's deep atmospheric dynamics rather than surface-driven weather phenomena. As Saturn's seasons progress toward northern spring and summer, the hexagonal storm undergoes subtle but measurable changes in its structure and appearance, its boundaries becoming more diffuse, and its internal circulation patterns shifting in response to increased solar heating of Saturn's northern hemisphere. The seasonal transformation occurs gradually across years, each change representing an incremental adjustment to altered atmospheric conditions, as solar energy input varies with Saturn's orbital position and axial tilt. The hexagon seasonal evolution demonstrates that atmospheric features operating on planetary scales can exhibit sensitivity to energy variations that would be negligible for smaller-scale weather systems. The hexagon seasonal variations may reflect changes in the atmospheric temperature gradients that maintain the geometric storm's structure, alterations in the precise balance of rotational forces, and pressure gradients that lock the atmospheric circulation into hexagonal geometry. As solar heating increases during northern summer, the temperature differences between Saturn's equatorial and polar regions diminish slightly, potentially altering the atmospheric jet streams that form the hexagon's boundaries and modifying the storm's internal circulation patterns. These seasonal adjustments occur within a geometric framework that remains fundamentally stable, suggesting that the hexagon represents a robust solution to Saturn's atmospheric dynamics that can adapt to changing conditions while maintaining its basic structure. Only took 15 years of Cassini observations to document the hexagon's seasonal cycle across half of Saturn's 30-year orbital period, revealing atmospheric dynamics that operate on timescales that challenge human patience and require sustained observational campaigns spanning decades to characterize fully. The seasonal changes demonstrate that Saturn's atmospheric system maintains memory of solar heating variations across years, integrating energy inputs over time, scales much longer than typical terrestrial weather patterns, creating atmospheric responses that lag behind the astronomical forcing by months or years as the massive atmospheric system adjusts gradually to changing conditions. The hexagonal storm's seasonal behavior may be linked to similar large-scale atmospheric phenomena that appear periodically in Saturn's temperate latitudes. Massive storm systems known as great white spots that emerge approximately once every Saturn year, creating planetary-scale atmospheric disturbances that can persist for months before dissipating into the background atmospheric circulation. These great white spots may represent seasonal manifestations of atmospheric instabilities that build up gradually over Saturn years before releasing their accumulated energy in spectacular storm outbreaks that temporarily alter the planet's global atmospheric circulation patterns. Saturn's seasonal atmospheric dynamics operate in an environment where the angular momentum of atmospheric circulation must be conserved across the entire planet, creating coupling between atmospheric features in different latitude bands that can transmit the effects of seasonal changes across vast distances through the planet's atmospheric system. The hexagon's seasonal variations may reflect changes in this global angular momentum budget, adjustments that propagate through Saturn's atmospheric circulation as the planet's overall energy balance shifts in response to orbital variations in solar heating intensity and distribution. The seasonal evolution of Saturn's hexagonal storm reveals the remarkable complexity that emerges when planetary-scale atmospheric systems interact with astronomical forcing cycles, creating weather patterns that blend atmospheric fluid dynamics with orbital mechanics in ways that produce phenomena unique to gas giant planets. The hexagon's seasonal adaptability demonstrates that even the most geometrically precise atmospheric features maintain dynamic flexibility, adjusting their structure and behavior in response to external forcing, while preserving their fundamental characteristics across decades of continuous operation. Scientists theorize that Saturn's hexagonal storm may exhibit variations on even longer time scales, possibly responding to changes in Saturn's orbital eccentricity or axial tilt that operate across thousands or millions of years, creating atmospheric evolution cycles that dwarf human civilization in their temporal scope. These hypothetical long-term variations remain beyond current observational capabilities, but they suggest that Saturn's atmospheric dynamics may preserve signatures of astronomical forcing cycles that operate across geological timescales, embedding the history of solar system orbital evolution within the planet's atmospheric circulation patterns. The hexagonal storm continues its seasonal dance through Saturn's long years, geometric precision adapting to astronomical rhythms that mark time on scales beyond human experience, atmospheric dynamics that blend fluid mechanics with orbital mechanics in the patient darkness, where planetary weather systems respond to the distant sun's influence across decades of slow seasonal change. Geometric beauty that persists through astronomical cycles in the cold depths where atmospheric mathematics creates patterns more perfect than any human architecture. In the deepest atmospheric layers of Jupiter and Saturn, where pressure climbs beyond human comprehension and familiar states of matter surrender to the crushing weight of entire planetary masses, gas gradually transforms into liquid through transitions so gradual that no clear boundary exists between atmospheric and oceanic phases of these gas giants' interiors. The crushing depths create pressure environments that exceed 1 million Earth atmospheres, conditions where hydrogen molecules lose their individual identities and merge into fluid continuums that behave according to physics that challenges terrestrial understanding of matter's behavior under extreme compression. At depths of 20,000 kilometers below Jupiter's visible cloud tops, atmospheric pressure reaches values that compress hydrogen gas to densities approaching those of liquid water. Yet, the material retains characteristics of both gaseous and liquid phases simultaneously, existing in a state that defies simple classification according to terrestrial phase diagrams. The hydrogen at these depths flows like liquid while maintaining the compressibility characteristics of dense gas, creating a fluid medium that exhibits properties intermediate between the familiar gas and liquid phases found under Earth normal conditions. Temperature at these crushing depths climbs to 6,000 Kelvin, hotter than the surface of the Sun. Yet the immense pressure prevents the hydrogen from expanding into the gaseous state that such temperatures would normally produce. The transition from gas to liquid occurs across thousands of kilometers of atmospheric depth, a gradual transformation where density increases continuously without discrete phase boundaries or sudden changes in material properties. This smooth transition creates atmospheric structures where the concept of a planetary surface becomes meaningless, where the distinction between atmosphere and interior blurs into arbitrary definitions based on pressure thresholds rather than fundamental changes in physical state. Jupiter and Saturn possess no solid surfaces in any conventional sense, instead exhibiting continuous pressure and density gradients that extend from the tenuous upper atmospheres to the compressed cores where matter adopts exotic configurations unknown to terrestrial experience. Saturn's atmospheric compression follows similar patterns, but achieves the gas-to-liquid transition at somewhat shallower depths due to the planet's lower overall mass and correspondingly weaker gravitational field. Yet even Saturn's shallow transition depths exceed 15,000 kilometers below the visible cloud tops, distances greater than Earth's diameter measured through atmospheric layers where pressure increases relentlessly with each kilometer of descent. The gradual nature of these phase transitions means that spacecraft descending through gas giant atmospheres would experience continuously increasing atmospheric density without encountering any definitive surface or boundary layer that marks the end of atmospheric flight and the beginning of oceanic navigation. Only took billions of years for gravitational compression to create these extreme pressure environments, transforming the simple hydrogen and helium of the solar nebula into dense fluid states that exist nowhere else in the solar system under natural conditions. States of matter that can only be approximated briefly in laboratory experiments that achieve extreme pressures for microseconds before the experimental apparatus destroys itself under the immense forces required to replicate gas giant interior conditions. The crushing depths operate as natural laboratories for extreme states of matter, creating material configurations that reveal fundamental properties of elements under conditions that push the boundaries of condensed matter physics. The atmospheric pressure at these extreme depths approaches the pressure found at Earth's center, yet the gas giant interiors achieve these crushing pressures through atmospheric compression rather than solid material compression, creating fluid pressure environments that span volumes larger than entire terrestrial planets, while maintaining the dynamic characteristics of atmospheric circulation rather than the static properties of solid planetary cores. The pressure gradients within gas giant atmospheres create buoyancy forces that drive convection currents spanning thousands of kilometers, circulation patterns that transport heat and material through pressure environments that would instantly crush any terrestrial material. The compressed hydrogen at extreme atmospheric depths begins to exhibit electrical conductivity as electrons become delocalized among hydrogen nuclei, creating the initial stages of the metallic hydrogen transition that occurs deeper within the planetary interiors. Yet this electrical behavior emerges gradually across atmospheric layers where matter retains fluid characteristics while acquiring metallic properties through the patient work of gravitational compression. The electrical conductivity increases continuously with depth, creating no sharp transition between insulating and conducting regions, but rather a smooth gradient of electrical properties that mirrors the smooth density gradient characteristic of gas giant atmospheric structure. Scientists calculate that the atmospheric pressure within gas giant interiors may exceed the pressure found at the center of smaller rocky planets, creating crushing environments where familiar chemical compounds decompose into their constituent atoms, where molecular bonds cannot withstand the compressive forces that reshape matter according to principles that operate beyond the comfortable scales of terrestrial chemistry and physics. These extreme pressure environments challenge current understanding of matter's behavior under compression, requiring theoretical models that extend beyond the pressure and temperature ranges accessible to terrestrial laboratories. The crushing depths continue their patient compression across atmospheric layers that stretch toward planetary cores, where pressure may reach tens of millions of Earth atmospheres, creating material states that bridge the gap between planetary atmospheres and stellar interiors. Compressed matter that flows according to fluid dynamics while exhibiting properties that approach those found in the cores of white dwarf stars. In the silent darkness where gravitational compression creates natural laboratories for extreme physics that operate beyond human scales of pressure and density. In depths where atmospheric physics merges with condensed matter, physics in the patient work of gravitational forces that have operated without pause since planetary formation. Phosphine molecules drift through the upper atmospheres of Jupiter and Saturn in concentrations that puzzle atmospheric chemists, their presence indicating unknown chemical processes operating in regions where conventional atmospheric models predict these compounds should not exist in detectable quantities. These unexpected molecular traces represent chemical fingerprints of processes occurring deep within the gas giant's atmospheric interiors, reactions that transport exotic compounds from high-pressure, high-temperature regions toward the observable atmospheric layers where spacecraft instruments can detect their spectroscopic signatures. The phosphine concentrations vary with atmospheric dynamics, suggesting active chemical production and transport mechanisms that operate across the vast vertical distances spanning gas giant atmospheric structures. Jupiter's atmosphere contains phosphine in abundance patterns that correlate with the planet's distinctive coloration zones, indicating that atmospheric circulation transports these molecules from interior chemical production regions toward specific latitude bands where upwelling currents carry deep atmospheric material toward the visible cloud layers. The phosphine distribution maps reveal the three-dimensional structure of Jupiter's atmospheric circulation, showing how convection patterns transport chemical signatures across thousands of kilometers of atmospheric depth. The molecular abundance variations provide chemical traces for atmospheric motion that would otherwise remain invisible to external observation, revealing circulation patterns that operate in the hidden depths where direct measurement remains impossible. Saturn's phosphine exhibits even more mysterious distribution patterns, with concentrations that vary seasonally in ways that suggest complex interactions between chemical production rates and atmospheric transport mechanisms that respond to seasonal changes in atmospheric circulation, strength, and direction. The seasonal phosphine variations operate on Saturn's 30-year timescale, creating chemical cycles that span human generations while reflecting atmospheric processes that integrate chemical production and transport across planetary scales. These long-term chemical cycles demonstrate that gas giant atmospheric chemistry operates as a planetary scale system where chemical processes in one atmospheric region influence molecular distributions across the entire atmospheric volume. The chemical pathways that produce phosphine in gas giant atmospheres remain largely mysterious, requiring high-temperature, high-pressure reactions that can break apart phosphorus-bearing compounds and reassemble them into phosphine molecules through processes that operate under conditions found only in the deep atmospheric layers where pressure exceeds thousands of Earth atmospheres. Laboratory attempts to replicate these chemical pathways require extreme conditions that can only be maintained briefly in specialized high-pressure chambers, providing limited insights into the sustained chemical processes that operate continuously within gas giant interiors across geological timescales. Only took decades of atmospheric spectroscopy to recognize the full extent of the chemical complexity hidden within gas giant atmospheres, revealing molecular inventories that include dozens of trace compounds whose presence indicates chemical processes operating under extreme conditions, processes that create molecular complexity through pathways unknown to terrestrial atmospheric chemistry. The trace molecule detection represents one of the most sensitive probes available for studying conditions within gas giant interiors, chemical signatures that reveal temperature, pressure, and circulation characteristics of atmospheric regions that remain inaccessible to direct measurement. Ammonia molecules also exhibit unexpected distribution patterns within both planets' atmospheres, with concentrations that vary vertically and horizontally in ways that indicate complex chemical equilibria operating under changing pressure and temperature conditions as atmospheric material circulates through different regions of the atmospheric volume. The ammonia variations provide additional chemical traces for atmospheric circulation, revealing how convection patterns transport chemical species across atmospheric layers, while chemical reactions alter molecular abundances according to the local thermodynamic conditions encountered during atmospheric circulation. Hydrogen sulfide detection in both atmospheres reveals the presence of sulfur chemistry operating under extreme conditions, creating molecules that form through high-temperature reactions between sulfur-bearing compounds and the abundant hydrogen that dominates gas giant atmospheric composition. The hydrogen sulfide concentrations provide insights into the sulfur inventory within gas giant interiors, chemical reservoirs that may represent material incorporated during planetary formation or created through subsequent chemical evolution processes that operate over billions of years within planetary atmospheric systems. The trace molecule chemistry within gas giant atmospheres operates as a form of natural atmospheric chemistry laboratory, creating molecular complexity through reactions that occur under pressure and temperature conditions that extend far beyond the range accessible to terrestrial atmospheric systems. Chemical processes that reveal fundamental aspects of molecular behavior under extreme conditions while providing unique insights into the chemical evolution of planetary atmospheres across geological timescales. Scientists theorize that the chemical complexity detected in gas giant atmospheres may represent only a small fraction of the total chemical diversity that exists within these planetary systems, suggesting that deeper atmospheric layers may support chemical processes that create molecular species too unstable or reactive to survive transport to the observable atmospheric regions where spacecraft instruments can detect their presence. The chemical mysteries persist in the observable atmospheric layers, while potentially greater chemical complexity remains hidden in the extreme conditions found within gas giant interiors. The phosphine molecules continue their vertical migration through atmospheric layers, where chemical production and destruction processes create molecular abundance patterns that vary across timescales ranging from atmospheric circulation periods to seasonal cycles. Chemical signatures that preserve information about conditions within the inaccessible depths, where unknown chemistry operates under pressure, and temperature conditions that challenge current understanding of molecular stability and reaction pathways. In the patient darkness where atmospheric chemistry creates molecular complexity through processes that operate beyond terrestrial analogies, Jupiter and Saturn radiate more energy into space than they receive from the distant sun, transforming these gas giants into self-warming worlds powered by ancient heat sources that have operated continuously since planetary formation 4.5 billion years ago. Jupiter emits 1.7 times more thermal energy than it absorbs from solar radiation, while Saturn radiates an even more impressive 3 times its solar energy input, creating thermal emission that makes both planets detectable by infrared telescopes as warm objects glowing against the cold background of interplanetary space. These excess thermal emissions represent the slow release of primordial formation energy, gravitational potential energy that was converted to heat when these massive planets first condensed from the solar nebula and began their long thermal evolution toward eventual equilibrium with their space environment. The heat sources within Jupiter's interior include leftover thermal energy from the planet's initial gravitational collapse, when the accumulation of hydrogen and helium from the solar nebula released gravitational potential energy equivalent to the fusion energy produced by a small star, heating Jupiter's interior to temperatures that still exceed 20,000 Kelvin at the planet's center, despite billions of years of cooling. This primordial heat slowly diffuses outward through Jupiter's atmospheric layers, transported by convection currents that operate across thousands of kilometers of atmospheric depth, carrying thermal energy from the hot interior toward the cold surface, where it radiates into space as infrared emission that has continued without interruption since Jupiter's formation. Saturn's thermal emission includes additional energy sources beyond simple primordial cooling, particularly the ongoing helium rain process that converts gravitational potential energy into heat as helium droplets sink through Saturn's interior, separating from hydrogen and concentrating in the planet's deeper layers while releasing energy equivalent to a sustained fusion reaction operating at planetary scales. The helium differentiation process began approximately 2 billion years ago when Saturn's interior cooled sufficiently for helium to become immiscible with hydrogen, initiating a gravitational energy release mechanism that may continue for billions of years into the future, providing Saturn with an internal energy source that supplements the thermal energy left over from planetary formation. Both planets cool according to thermal evolution models that predict gradual temperature decline over billions of years. Yet the cooling process operates so slowly that Jupiter and Saturn will remain warm, thermally active worlds for billions of years beyond the eventual death of the Sun, continuing to radiate internal heat long after solar energy ceases to warm the inner solar system. The thermal evolution timescales for gas giant planets extend far beyond stellar main sequence lifetimes, creating worlds that will outlive their parent stars while maintaining internal energy sources that operate independently of external heating. self-sustaining thermal systems powered by gravitational energy stored during planetary formation. Only took billions of years for these ancient heat sources to establish their slow, steady energy release patterns, each thermal emission representing one small increment in cooling processes that will continue for tens of billions of years before Jupiter and Saturn reach thermal equilibrium with the cosmic microwave background radiation that permeates intergalactic space. The thermal evolution operates as a form of planetary memory, preserving information about formation conditions and early solar system dynamics within the temperature structure of planetary interiors that cool according to physical laws that operate across astronomical timescales. The internal heat drives atmospheric circulation patterns that would not exist if these planets depended solely on solar heating, creating convection systems and weather patterns that operate independently of seasonal variations or solar energy input changes. Atmospheric dynamics powered by internal energy sources that maintain consistent strength across orbital periods and seasonal cycles. The internal heating creates atmospheric temperature gradients that drive winds, storms, and circulation patterns across atmospheric volumes that dwarf terrestrial weather systems. Global atmospheric dynamics sustained by planetary-scale energy sources that operate with the patience of geological processes. Jupiter's thermal emission varies slightly with atmospheric dynamics, as convection patterns transport heat from the interior toward the surface with varying efficiency, creating thermal variations that correlate with atmospheric circulation changes and storm system evolution, linking internal heat transport to observable atmospheric phenomena through complex feedback mechanisms that operate across planetary scales. The thermal emission measurements provide insights into internal structure and heat transport processes that would otherwise remain inaccessible to external observation, revealing how heat moves through planetary interiors according to convection patterns that span thousands of kilometers of atmospheric depth. Saturn's thermal emission exhibits variations that correlate with the planet's seasonal cycles and helium rain processes, creating thermal signatures that reveal the complex interactions between multiple energy sources operating within the planet's interior. Energy release mechanisms that include primordial cooling, helium differentiation, and gravitational compression effects that combine to create Saturn's overall thermal budget. The thermal emission variations provide clues about internal processes operating in regions where direct measurement remains impossible. Internal energy sources that shape atmospheric dynamics while remaining hidden within the planetary interior. Scientists calculate that Jupiter's internal temperature will remain above 1000 Kelvin for approximately 50 billion years, long after the Sun expands into a red giant and eventually becomes a white dwarf star, creating a scenario where Jupiter continues to emit thermal radiation in a solar system illuminated only by the fading light of stellar remnants, a warm world powered by ancient gravitational energy in a universe grown cold and dark around the dying solar system. The ancient heat sources continue their patient energy release through atmospheric layers that transport thermal energy across thousands of kilometers of depth, internal energy flowing outward through convection patterns that have operated since planetary formation, thermal emission that marks the slow cooling of worlds that store gravitational energy on scales that dwarf human comprehension. In the darkness, where planetary interiors practice their own forms of energy conservation across timescales that extend beyond stellar evolution. In the deepest atmospheric layers of Jupiter and Saturn, beneath all the turbulence and storm systems that characterize the visible surfaces, beneath the lightning and winds and swirling vortices that capture human imagination, lies a realm of crushing silence where atmospheric motion slows to the patient rhythms of geological time, and pressure creates a stillness more profound than any earthly quiet. These depths exist beyond the reach of atmospheric circulation, Beyond the influence of solar heating or seasonal variations, in regions where the very concept of weather dissolves into the slow, inexorable processes of planetary scale fluid dynamics operating under pressures that transform matter itself according to physics that operates beyond human scales of experience. The silence emerges gradually as atmospheric depth increases and pressure climbs beyond the threshold where sound waves can propagate through media so dense that acoustic vibrations become absorbed by the material properties of compressed hydrogen and helium gas approaching liquid densities, at pressures exceeding 100,000 Earth atmospheres. The atmospheric medium becomes so dense that sound transmission requires energy levels beyond those available from typical atmospheric motion, creating acoustic dampening that produces a quiet, more complete than any silence found in terrestrial environments. A stillness that has persisted unchanged since the formation of these planetary atmospheres billions of years ago. The crushing depths create pressure environments where atmospheric turbulence cannot maintain itself against the viscous forces that emerge when gas density approaches liquid values, where the Reynolds numbers that characterize fluid flow drop below the critical thresholds necessary for turbulent motion, creating laminar flow conditions that extend across planetary scales in regions where atmospheric circulation operates according to viscous fluid dynamics rather than the inertial turbulence that characterizes gas giant upper atmospheres. The transition from turbulent to laminar flow occurs gradually across thousands of kilometers of atmospheric depth, creating layers where atmospheric motion becomes increasingly organized and predictable as pressure and density increase. Jupiter's deepest atmospheric layers exist in a state of quasi-hydrostatic equilibrium, where gravitational forces balance pressure gradients with such precision that vertical motion becomes negligible compared to the slow horizontal circulation patterns that transport heat and material across planetary distances through convection cells that operate on timescales measured in millions of years. These deep circulation patterns move atmospheric material at velocities measured in centimeters per year, flows so slow that individual parcels of atmospheric gas may require geological time spans to complete single circulation cycles through Jupiter's interior atmospheric structure. Saturn's deep atmospheric regions exhibit similar characteristics of profound stillness, punctuated only by the slow descent of helium droplets that fall through the dense medium like raindrops falling through honey, their motion creating the only significant vertical transport processes operating in atmospheric layers where pressure has eliminated all other forms of atmospheric circulation. The helium rain creates gentle stirring motions in the otherwise motionless deep atmosphere. Mechanical mixing processes that operate at velocities so slow that they barely disturb the fundamental quiet that characterizes Saturn's deepest atmospheric layers. Only took billions of years for these deep atmospheric regions to achieve their current state of near-perfect stillness. Gravitational compression gradually eliminating the energy sources that drive atmospheric motion until only the most fundamental circulation processes remain active in regions where atmospheric dynamics operate according to diffusive transport rather than convective circulation. Molecular scale processes that move heat and material through media so dense that bulk fluid motion becomes energetically prohibitive. The stillness extends across atmospheric volumes larger than entire terrestrial planets, creating vast regions of space where motion occurs only on molecular scales, where the dramatic storm systems visible from space represent merely surface expressions of atmospheric dynamics that fade into insignificance with increasing depth, until atmospheric activity becomes indistinguishable from the slow molecular processes that characterize planetary interior evolution rather than atmospheric circulation. The quiet depths preserve conditions that may have remained essentially unchanged since planetary formation. Atmospheric layers that serve as repositories for primordial atmospheric composition and structure. Temperature gradients in these deep regions approach adiabatic values where heat transport occurs primarily through conduction and radiation rather than convection, creating thermal equilibrium conditions that eliminate the temperature differences necessary to drive atmospheric circulation. Thermal balance that contributes to the profound stillness characterizing these atmospheric depths. The thermal equilibrium creates atmospheric layers that exist in states approaching thermodynamic equilibrium. Regions where entropy production approaches minimal values and atmospheric evolution proceeds according to the slowest possible rates consistent with fundamental physical laws. The crushing silence encompasses regions where atmospheric pressure creates material densities that approach those found in planetary cores, where the distinction between atmospheric and interior processes becomes arbitrary, where atmospheric science merges with condensed matter physics in the study of material behavior under extreme conditions that exist nowhere else in the solar system under natural circumstances. Conditions that reveal fundamental properties of matter under compression while creating environments that challenge the boundaries between atmospheric and planetary interior science. Scientists theorize that these quiet depths may preserve chemical and isotopic signatures from the early solar system, atmospheric layers that have remained isolated from surface processes for billions of years, creating natural archives of primordial atmospheric composition that may contain information about conditions in the solar nebula from which these planets formed. Chemical records preserved in the stillness where atmospheric mixing operates on timescales longer than the age of the solar system. The quiet between storms extends through atmospheric depths where pressure creates a stillness more profound than interstellar space. Regions where the absence of motion becomes a fundamental characteristic of atmospheric structure, where silence emerges from the patient work of gravitational compression across billions of years, in the crushing depths where atmospheric dynamics surrender to the deeper physics of matter under extreme pressure, in the darkness where planetary atmospheres practice their own forms of profound quiet. The atmospheric depths of Jupiter and Saturn continue their eternal dance in silence, rotating with their ancient planets through space that has grown familiar across 4.5 billion years of orbital motion around a star that burns with steady patience in the cosmic darkness. The hidden storms and lightning, the diamond rain and helium droplets, the metallic hydrogen seas and crushing pressures, all exist in perpetual motion beneath cloud tops that have swirled in patterns older than life itself. Atmospheric processes that operate according to physical laws written in the fundamental language of gravity and thermodynamics. In these depths where no human observer will ever venture, where pressure transforms matter into states unknown to terrestrial experience, the gas giants practice their slow alchemy of elemental transformation and atmospheric circulation, converting the simple hydrogen and helium of their formation into complex chemical networks and exotic material phases through the patient application of gravitational compression across geological time. The planets warm themselves from within while cooling gradually toward distant equilibrium states that will not be reached for billions of years beyond the eventual death of the Sun. The storms that rage across their visible surfaces draw energy from sources buried in crushing depths, where metallic hydrogen generates magnetic fields that stretch across millions of kilometers of space, where atmospheric circulation operates according to rhythms measured in planetary years rather than terrestrial seasons, where the geometry of hexagonal storms and the persistence of ancient hurricanes reveal the mathematical beauty that emerges from fluid dynamics operating on planetary scales under the influence of rapid rotation and internal heating. Jupiter and Saturn guard their secrets in atmospheric layers that extend deeper than the diameter of Earth, in regions where the familiar becomes alien and the physics of compressed matter challenges human understanding while revealing the fundamental processes that govern planetary evolution across astronomical timescales. The missing water and unexpected chemistry, The seasonal variations and gravitational archaeology all point toward complexities that operate beyond current theoretical frameworks, mysteries that persist in the observable atmospheric layers, while potentially greater mysteries remain hidden in the extreme conditions found within gas giant interiors. The quiet that exists in their deepest atmospheric layers represents a stillness more profound than any earthly silence. Regions where atmospheric motion slows to the patient rhythms of geological time and pressure creates conditions of near-perfect thermal and mechanical equilibrium, where the dramatic weather systems visible from space fade into insignificance beneath the crushing weight of planetary atmospheres that extend toward cores where matter adopts forms that exist nowhere else in the known universe. These gas giants continue their orbital dance around the Sun while rotating with periods measured in hours, carrying their hidden atmospheric depths through space and time with the persistence of planetary-scale processes that operate independently of human observation or understanding. Atmospheric systems that preserve information about solar system formation while evolving according to internal dynamics that unfold across billions of years. In the patient darkness, where planets practice their own forms of slow, elemental transformation. In the stillness between storms. In the crushing depths where diamond rain falls through metallic hydrogen seas. In the geometric precision of hexagonal hurricanes and the ancient persistence of great red spots. Jupiter and Saturn continue their atmospheric evolution with the unhurried patience of geological time. Atmospheric processes that connect planetary formation to distant futures, when these worlds will still radiate internal heat in a universe grown cold around them, warming themselves with ancient energy in the eternal quiet of space.